Hello friends, I welcome you in lecture number 19 on group theory. In this lecture also we will discuss one example on finding cosets of subgroup of a group. Before going for that example, we just take a note on this. Suppose we have Abelian group and we want to find out cosets of a subgroup of Abelian group, then this result says that if you have Abelian group, then left cosets and right cosets are equal for every element of a group. So simple meaning is the left and right cosets of a subgroup H are equal if given group is Abelian. So whenever you are asked to find out left as well as right cosets, you can check whether your group is Abelian or not, and if you are sure that your group is Abelian, then you can use this result. You can first find out left cosets, and because left and right cosets are equal, you can directly write down the right cosets also. So we consider one example. Here we are given group of integers under standard addition, and subgroup is this set of multiples of 4z, and we have to find out left and right cosets of H in G. So first we write down this H is given as 4 times z. That means we collect all those integers which are multiples of 4. So we can write that 4m, where m belongs to z, or we can list out some of the multiples. We start with 0, then 4, then 8, 12 and so on, and on this side we write negative integers -4, -8, -12 and so on. So this is infinite set, and this group of integers is also infinite. We have to find out left and right cosets of H in Z. We can write the description of Z also, because we have to decide the cosets for every element of group Z, and operation is standard addition: -1, -2, -3, -4 and so on. So we start with the element 0. We decide the left coset of this H for this element 0 of given group Z, and operation is standard addition. So first we write down this left coset corresponding to element 0, and because our operation is addition operation, we write 0 plus H. And if you remember the properties of cosets which we have discussed in the last lecture, so we have this one property which says that if an element A is member of given subgroup, then left coset corresponding to that element is that subgroup itself. And here we can see 0 is a member of this subgroup H. Therefore 0 plus H will be equal to H itself. So let me write this H, 4, 8, 12 on this side, and -4, -8, -12. So this is the left coset corresponding to the element 0. Now we know that this group of integers under addition is Abelian. We know that for any two integers this property is satisfied: m plus n equal to n plus n for all possible values of m and n. So this group is Abelian. Therefore left coset corresponding to 0 and right coset corresponding to 0 are same. So we can write that right coset H0, or we can write H plus 0. This is also equal to 0H, which is H. And here we can mention that because Z with operation addition is abelian. So we don't have to calculate right coset. Now we find out left coset corresponding to element 1. So we consider 1h, operation is addition. So here we write 1 plus h, and 1 is not a member of this subgroup h. So we go by definition. 1 plus h equal to, we consider this type of elements 1 plus h, where h belongs to 4z, that is our subgroup h. This is by definition of left coset. And here elements of this h are in this form: 1 plus 4m, and m is any integer, or we can add 1 to each of these multiples of 4. If we want to write in this another form, we can start by adding 1 to each of these elements. So 0 plus 1, that is 0. We can concentrate here also. 0 plus 1, then 4 plus 1, 8 plus 1, 12 plus 1, and so on. Here minus 4 plus 1, that is minus 3, minus 8 plus 1, that is minus 7, minus 12 plus 1, that is minus 11, and this will continue in negative direction also. This is the left coset corresponding to the element 1, and because our group is abelian, this is right coset corresponding to 1, which we can denote by h plus 1 or h into 1. Now we go for this element 2. Now 2 is not the element of h, so we check for 2 also. We find out what is the left coset corresponding to 2. So we write down by definition. We have to find out this type of elements 2 plus h, where h belongs to capital H, that is 4z, or we can simply write h also. So this means I have to consider 2 plus 4m. Elements of h are in this form, where m belongs to z, and we can put different values of m to write down some of the elements. Suppose I take m equal to 0, I will have 2. For m equal to 1, I will have 6. For m equal to 2, I will have 8 plus 2, that is 10. And you can notice the difference here. Difference of any two successive elements is 4. 2 plus 4 is 6, 6 plus 4 is 10, 10 plus 4 will be 14. If we take negative value of m, suppose I consider m equal to minus 1, then this is minus 4, and 2 minus 4 is minus 2. For m equal to minus 2, I will have 2 minus 8, that is minus 6. For m equal to minus 3, I will have 2 minus 12, that is minus 10, and so on. This is the left coset corresponding to element 2, and because our group is abelian, it is right coset also, which we can denote by h plus 2 or simply by h times 2. Okay, fine. So now we go for left coset corresponding to the element 3. So for 3 also we have to go by definition, because 3 is not present in any of these left cosets. Okay, we can check whether 3 is present somewhere here, so that we can use another property, but 3 is not present in any of these left cosets. Okay, because we know this property, that if some element is a member of subgroup, member of left coset, suppose A1 belongs to the left coset corresponding to element A2, then we know that left cosets corresponding to A1 and A2 are equal. So this is the reason I am checking whether 3 is present in any of these left cosets or not. So here 3 is not present, here also 3 is absent, here also 3 is absent. So I have to find out left coset corresponding to 3 by the definition 3 plus h. This is by definition 3 plus small h, where small h is element of given subgroup, which is 4z, and elements of 4z are in this form 3 plus 4m, where m is any integer. So we write down sum of these elements. For m equal to 0 we will obtain 3, for m equal to 1 we will obtain 7, for m equal to 2 we will obtain 8 plus 3, that is 11, and so on. For m equal to minus 1 we will have 3 minus 4, that is minus 1. For m equal to minus 2 we will have 3 minus 8, that is minus 5. For m equal to minus 3 we will have 3 minus 12, that is minus 9. And you can notice that difference of any two neighboring elements is 4. Here we can see the difference of 11 and 7 is 4, difference of 7 and 3 is 4, difference of 3 and minus 1 is also 4, difference of minus 5 and minus 9 is also 4. So if we observe this, we can write down only one element, and then we can write previous element by adding 4 and succeeding element by adding 4 and previous element by subtracting 4. Okay, fine. Now we check for 4. Now we are interested in the left coset corresponding to 4. So before going by definition, we will check whether this 4 is present somewhere or not, whether this 4 is present in any left coset or not. So we can observe that 4 is present here. 4 is an element of left coset corresponding to 0. Therefore we can say that left coset corresponding to 4 will be equal to this one, 0h. And of course I should write down here this is equal to right coset also, because group is Abelian. So now we mention that 4 is a member of this left coset. This implies left coset corresponding to 4h will be equal to 0h, that is h. Similarly, next element is 5, and we can see that 5 is present in this element, this left coset. 5 belongs to 1h. 5 is a member of left coset corresponding to 1h. Therefore left coset corresponding to 5 will be equal to left coset corresponding to 1. Similarly, we can observe that 6 is present in this. So left coset corresponding to 6 will be equal to left coset corresponding to element 2. And same thing we can observe for negative elements. Suppose I want to check for minus 1, then I will search the left coset which contains minus 1. So this left coset contains minus 1. Minus 1 is an element of 3h. Therefore left coset corresponding to minus 1 will be equal to left coset corresponding to 3. So now if we continue in this way, all these left cosets are repeating. Left cosets corresponding to 0, 1, 2 and 3, and for remaining elements all these cosets are repeated. So there are only 4 distinct left cosets, as well as there are only 4 right left cosets, because our group is Abelian. So we can write that there are only 4 distinct left cosets of subgroup H equal to 4Z as listed below. And we can parallelly write for right cosets also. So those left or right cosets are, first one was 0h, or we can write 0 plus h, then 1h or 1 plus h, 2h or 2 plus h, and 3h or 3 plus h. And similarly, right cosets are equal 1h, which is equal h1, that is h plus 1, which is equal to, first we write for 0, or we can write directly here also because they are equal. So we can write this is equal to h plus 0, that is h0, or h plus 1 equal to h1. Right coset corresponding to 2 is equal to left coset corresponding to 2, and right coset corresponding to 3 is the same as left coset corresponding to 3. So here we are asked to find out left and right cosets of this subgroup H equal to 4Z in this set of integers, and we have used properties of left cosets and right cosets as well to write down the 4 distinct left as well as right cosets. And if you observe, if you take union of all these left cosets or right cosets, then they will form a partition of Z. If you take union, then you will get set of integers. You can see I can start with 0. 0 is member of left coset corresponding to this 0 element. Then 1 is the member of left coset corresponding to 1. 2 is the member of left coset corresponding to 2. 3 is the member of left coset corresponding to 3. And 4 is the member of left coset corresponding to 0. 2 is the member of left coset corresponding to 2. So if we take any element of Z, then it will be present in some left coset. For some element B, it will be present there. So in that way we can check that this set of integers is the union of all these 4 distinct left cosets, and all these left cosets, this 0h, 1h, 2h and 3h, we can observe that if we take any of these 2 left cosets, then they are disjoint and their union is the set of integers. Okay, fine. So here we just have to decide what are the left and right cosets of subgroup 4Z in the set of integers. So you have to write up to this. There are only 4 distinct left cosets of H as listed below, and you can write in the bracket because our group is Abelian. So this is all about this session. I hope you like it. Thanks for